When a parallel plate capacitor is connected across a DC battery, explain briefly how the capacitor gets charged. Okay. When the capacitors are connected in parallel with the DC source, the charging of capacitor, the plates gets charged in accordance with the terminals of the battery, so that the potential difference between the plates will become equal to the terminal potential of DC battery. Okay. Second part. A parallel plate capacitor of capacitance C is charged to V volt by a battery. After some time, the battery is disconnected and the distance between the plates is doubled. Now a slab of dielectric constant K greater than 1 and less than 2 is introduced to fill the space between the plates. How will the following be affected? Here the first one, the electric field between the plates of the capacitor, the energy stored in the capacitor. Justify your answer in each case. Okay. Now, the electric field between the plates of the parallel plate capacitor is given by, that is a part B. In this first one, the electric field between the plates of a parallel plates capacitor, which is given by E naught, that is given by E naught is equal to sigma divided by epsilon naught, which is equal to, we can write it as a Q divided by epsilon naught times A, where sigma is nothing but Q by A, where sigma is equal to the surface charge density. If the dielectric is inserted, then E is equal to Q divided by epsilon naught times A into K. Then we can write this one as E naught divided by K, where K is a dielectric constant and hence electric field intensity decreases to 1 by K times. Okay, here this is decreased to 1 by K times. Second part, the energy stored in the capacitor. The part B, the second part, the energy stored in the capacitor. Effect on energy stored in the capacitor. Since the energy stored in the capacitor is given as U is equal to Q square divided by 2C. U is equal to Q square divided by 2 times C, which is equal to Q square D divided by 2 times epsilon naught A, where C is equal to epsilon naught A divided by D, where D is the distance between two plates. Similarity, if U dash is equal to Q dash divided by 2C, that is U dash is equal to Q dash divided by 2C, which is given as Q squared D1 divided by 2 times K, that is K into epsilon naught into A, and U dash is equal to 1 by K times Q square 2D divided by 2 into epsilon naught A. That is, we can write this one again same as U dash is equal to 1 by K times Q square 2D divided by 2 into epsilon naught times A, and U dash is equal to 2U by K. Therefore, I is less than K and less than 2. That is, U dash is equal to 2U by K. Then we can say this one as I is less than K and it is less than 2. Then we can read K is greater than I and less than 2. Therefore, the energy stored between the plates increases. The energy stored between the plates are increases. The electric potential as a function of distance x is shown in the figure. Draw a graph of the electric field E as a function of x. Okay, this is the graph they are going to show here. Here the velocity, that is the potential, is increased from 0 to 1. Then 1 to 2, it is the potential, it is the same, that is constant. Then 2 to 3, again it is decreased in the potential. Okay, then we need to find the electric field graph we need to plot here. So we know that V is equal to K times X, where K is the slope, here. Then we can see that V is directly proportional to the X. Then E is equal to, we know that energy E is equal to minus dV by dx. If I were to put this X value with that is then this becomes, that is the distance potential is increases. Here the potential value 0 to 1 it increases. Then we can write E is equal to minus d by dx of kx. Then the value becomes minus k. The value is minus k here. Okay. Then from 1 to 2 here, the potential, the distance of the potential, it is the same. Here potential difference, it is the same. That means there is no change in the potential difference. Then we can write this one as E is equal to dV by dx is equal to 0. That is constant. There is no change here. Then from 2 to 3, if you are going to take, then the potential difference, it gradually decreases. That is the minus value. That is V is directly proportional to the minus x. V is directly proportional to minus x. Then V is equal to, you can write V is equal to minus k times x. Then this becomes k value. That means here it becomes the positive value. Then if you are going to plot the graph here, the graph will be looks like this. Okay, initially from 0 to 1, it is a minus k. That means 0 to 1, it is a minus value, it is increased up to here. Then 1 to 2, it is gradually, there is no potential difference, it is a constant. So 1 to 2 it is the same. And 2 to 3, it is a plus k. That means it will increases like this. Derive an expression for the potential energy of an electric dipole in a uniform electric field. Explain conditions for stable and unstable equilibrium. Okay, first we will see the potential energy of an electric dipole diagram. If you are going to see this diagram, you can see here this is the electric charge. It is moving in this direction. Electrical charge is moving in this direction. And where if I am going to take the dipole of minus q to q, the distance is 2a. Minus q to q, the distance is 2a. And with an angle theta. Okay. And if I am going to rotate this one in the, okay, this direction, then the alpha cos theta, and here it is the minus a cos theta. Okay, the opposite direction, if I am going to rotate, the value I am getting like this. Then we know that since the torque acting on a dipole, that is the tau vector is equal to P vector into E vector. Okay, then tau is equal to Pe sin theta into n. Tau is equal to Pe to sine theta into n. Sine theta into n. We'll rotate in the sine theta angle. Then d omega is equal to 2 times d theta. Then tau is equal to Pe sine theta into d theta. If I were to integrate with theta 1 to theta 2, then work dw, that is w is equal to integration with respect to theta 1 to theta 2, then this is dw, then we'll get Pe, if I were to take it as a constant, that is a Pe into integration theta 1 to theta 2 sine theta into d theta. Okay, then w is equal to Pe minus cos theta. W is equal to Pe times minus cos theta. Okay, then if I am going to apply the limits here 1 to 2, then this becomes Pe into cos of theta 1 minus cos of theta 2. Okay, then theta 1 is equal to 0, theta 2 is equal to 0, then w is equal to Pe into cos of what that is, it becomes 1 minus cos theta. 1 minus cos theta. This is the work done equation. Okay. Then explain the conditions for stable and unstable equilibrium. For conditions for stable and unstable equilibrium, when electric dipole is a parallel to the electric field in stable equilibrium, and for unstable equilibrium, anti-parallel to electric field. Okay, and here the part B question: is the electrostatic potential necessarily zero at a point where the electric field is zero? No. Okay, give an example to support your answer. So answer for this one is that no, because inside an equipotential surface. Okay, that means if I would take that, we know that energy is equal to minus dV by dr, where V is equal to the constant, then we can write that one as E is equal to minus dk by dr, where r is the radius or distance. That is E is equal to minus dV by dr, where V is equal to the constant value here, and we can write E is equal to constant value, that is minus dk by dr, where r we call this is the distance or radius. This is the distance or radius. Okay, then this whole will become where it becomes 0. Then the electrostatic potential is 0 at a point where the electric field is 0. It is no, it is not possible. Okay, becomes